Good morning. So today our topic is relations, functions and binary operations. This topic is important for IIT JEE exam. One or two questions they will ask from here for sure, and that too, these types of questions is easy only. So we have to concentrate on this chapter very much. Let's start. So I'll start from the relation. What is relation? We can have this word many times in our real life, like in our home only. I have my father, mother, sister, brother. So what are these? These are the relations. So in mathematics, we need some operations, we need some symbols to relate this, because in the whole mathematics, what are numbers? Suppose I am saying 1 is a natural number, so 1 is related to natural number, 1 is real number, so 1 is related to the real number as well. So in this mathematics, we have symbolized the relation. Let's see, I am taking one example first. Suppose we have a family. It is a family and it is also a family. Here we have father, mother, brother, sister. Here we have father, mother, brother and sister. So father and mother is related as wife husband. The relation is wife husband. Mother and father, wife husband. Brother and father. Brother is the son of father. The father and brother are related. Father and sister are related. So mother and father, mother and brother, mother and sister. These all are related. So similarly we can say son and father, son and mother, son and brother are related. If I give son to son, then that will represent itself only. So we can say here, this is a relation on this family. This set is called the domain. In our technical words, this set is called codomain. And the terms which are related to here is called the range. So here the domain I can write father, mother, brother, sister. The codomain I can write father, mother, brother and sister. Range means which element is connected to this, then that will be called the range. So here all elements we can see connected, so we will write father, mother, brother and sister. So this is a relation on this family in which domain is this force, codomain and range is like this. Let's take the other examples. And also here we can write, we can define the relation R. We write in symbolic form on the pair of members such that X is father of Y. We write the relation in this form, symbolic form. Here, what all elements will belong to this relation on this family? X is father of Y. So here, father, brother and father, sister will belong to this relation. Why? Because father, X is the father of Y, means father is the father of F, is the father of B, F is the father of S. So in this relation we have two elements. What is the domain of this relation here? Father. What is the range of this relation here? Brother and sister. And the codomain will be unchanged, that is father, mother, brother, sister. So this is how we represent in any family. Let's see the other more technical words in this. Suppose we have a question given, there is a relation R which is defined on the set of natural numbers such that the pair xy is equals to y equals to x plus 1 and xy both are less than equals to 3, greater than equals to 1, and R is defined on set of natural numbers. Suppose R is a relation on the pair of number xy such that y equals to x plus 1 and x and y both are going from 1 to 3, and R is defined on the natural numbers. Capital N means natural numbers. So here we have to find the domain and range for this relation. Find domain, range and codomain for this relation R. Suppose we have to find this. Let's see. To find the domain, range and codomain, let's draw the pictorial diagram that will be helpful. We have here two sets. Here I am saying this A and this I am saying B. So here some elements will be there, here some elements will be there. Now R is defined on the natural numbers, so x and y we can take 1, 2, 3, 4. We can't take 0, minus 1, minus 2 because those are not natural numbers. So take x equals to 1. So if x equals to 1, the y value from here will become 2. Suppose we have 1, 2, 3, 4, 5, so on we have all natural numbers. Now 1 is related to 2. Now put x equals to 2. 2 will be related to 3. Now if we take 3, that will be related to 4. But here we have to be careful. Here the question is saying relation is defined where this is satisfying this condition as well. Means x and y should be belonging to 1 to 3. Here if I take 3 in set A, that will not be related to in set B. Why? Because we will get 4 and the question is saying y should not be equals to 4. So this element will not be a part of this relation. Hence, now we can say the domain of this relation as 1 to only, the range of this relation as 2, 3, and codomain. Codomain of this relation as all natural numbers. That is what I was talking about. Codomain will include all the numbers on which the set is defined. Only the related one will be the range of the relation. That is how we find the domain and range for any relation. Let's see the next question. Now, suppose R is a relation on a set xy such that mod of x equals to mod of y, x and y belongs to natural, and x is less than equals to x and y less than equals to 3, greater than equals to 1. Let me take it all integers, and here I want to take minus 3. Let's say this question. Suppose R is a set, R is a relation on the whole integers. R is defined on all integers. Suppose we have this question. R is a relation defined on the pair xy such that mod of x equals to mod of y, x and y are integers, and this is satisfying this condition. X, y is lying from minus 3 to 3 and R is defined on I. Then we have to find domain and range of this relation. Codomain will be all integers Let's see, the same way we will go. Suppose we have set A, set B. Now let's say we will take sum. Now x I can take -3 here, and here the y value we will be taking. Now corresponding to -3 here in A, -3 mod and 3 mod both are same. Suppose I am taking here -3, -2, -1, 0, 1, 2, 3 and so many all integers it will contain. And here the domain we have -3, -2, -1, 0, 1, 2, 3 only. This is the domain. Now -3 will be related to mod of x should be mod of y. So -3 will be related to -3 as well as it will be related to 3. Why? Because mod of -3 equals to 3 only. So here mod of y, that is mod of -3 and mod of 3 will be same only. Now similarly -2 mod will be related to -2 as well as 2. Similarly 1 -1 will be related to -1 as well as 1. 0 will be related to 0 only. 1 will be related to -1 and 1. Similarly 2 will be related to 2 and -2. 3 will be related to 3 and -3. So this is the scenario of this relation. So if I say what is the domain? Domain is all this set. What is the range? Range is also in this set. Here we can say range is equals to domain. But here the codomain will be all the integers. In some technical words we have this -3 is the image of -3 and 3 as well. And this -3 and 3 are the pre-image of -3. This is the some technical terms. Image means that side, pre-image means this side. Let's see more on this chapter. Now the most important part of this chapter is types of relation, and from there we will get one question for sure. Types of relation. The first type is void relation, or it is also called null relation or empty relation. As the name suggests, it will have, this relation will have no element, and we know from the set theory that phi belongs to every set. So this phi will belongs to, phi is a subset of every set that we know from the set theory. So phi will be, because relation is nothing but a set only, so phi will be a subset of this relation. This type of relation is called null relation, means this relation will contain no elements. The second is universal relation. Suppose we have a set A. R is defined on set A. Suppose we have a relation defined on this set A. Then if you calculate A cross A, then it will contain all the possible elements which will belongs to this relation. This will be for sure a relation in R, 100%. So every set is a subset of itself, hence this relation will be always a relation on this set A. Hence this is called the universal set. Universal in the sense that it will be always a subset of itself. That's why it is very obvious. That's why we term it in relation as universal relation. In case of set theory, it is called the universal set. The same concept here. Now let's see the other types. Now other type we have reflexive relation. See, what is the reflexive relation? If in any relation every set is connected to itself, then that is called the reflexive relation. Means every element related or connected in the diagram to itself for all A belongs to A. Every element related to itself on this relation, then that is called the reflexive relation. For example, suppose we have a set A as 1, 2, 3, 4, and we have a relation R1 as 1, 1, 2, 1, 3, 3, 2, 2. Then can we say this R1 relation on set A as reflexive? See, every element in set A should be related to itself. 1 is connected to 1, yes. 2 is connected to 2, yes. 3 is connected to 3, yes. 4 is connected to 4, no. Hence, this is not a reflexive relation on this set A. Let's see the other example. Suppose I am taking the relation in ordered pair as like that. Is this a reflexive relation on this set A? Let's check. 1, 1, yes. 2, 2, yes. 3, 3, yes. 4, 4, yes. Hence, this is the reflexive relation on this set A. Let's see other example. On this set only, I am defining the relation 1, 1, 2, 2, 3, 3, 4, 4, 1, 2, 3, 4. Is R3 a reflexive relation on this set A? Let's check. 1, 1, 2, 2, 3, 3, 4, 4 is there. But we have other elements as well. So it doesn't matter whether other elements are there or not. Only in the definition is every element should be connected to itself. That is there in R3. Hence, it is a reflexive relation. That is how we define the reflexive relation. Let's see the next example. A real-time example we will take on this reflexive relation. See, other example I am taking. Suppose set A is every triangle in a given plane, and the relation is here I am defining triangle 1 is congruent to triangle 2 such that triangle 1 is congruent to triangle 2, where this triangle it belongs to this set. Now see this relation. This relation is saying that this relation is defined on this set A, and the relation here is this triangle 1 is congruent to triangle 2. Can we say it as reflexive relation? Let's see. Here, if we check, every triangle is congruent to every triangle. Is it true? Every triangle is congruent to every triangle. Yes, of course it is true. Because suppose we are drawing one triangle A, B, C, and the same triangle I am saying it as A dash, B dash, C dash. So triangle ABC will be congruent to triangle A dash, B dash, C dash for sure, because by SSS property, SAS, whatever we take, both are same only. So this will have to be congruent. Hence this relation is the reflexive relation. Let's see next. Now the fourth type of relation is symmetric relation. Let's see how to define it. This relation says if AB belongs to this relation, then BA should belongs to R. This is the condition for a relation to be symmetric relation. Let's see some examples. Suppose R is a relation which is, we are defining here, the pair of numbers xy such that x equals to y, where x and y belongs to R, real numbers. Now see, here we are defining this relation on this set A as a pair xy such that x equals to y. So now see, if x equals to y, do we have y equals to x? If x equals to y, then we have y equals to x. Yes, it is obviously true. Hence, this relation will be the symmetric relation. Let's see more example. Suppose we have a set A as set A, we have 1, 2, 3, 4. And here I am defining some relation and which we have to state whether these are the relations on this set A symmetric or not. The R1 relation I am taking 1, 2, 2, 3, 2, 1, 3, 2. R2 relation I am taking as 1, 2, 3, 4, 2, 1, 4, 3. See, now we have to check whether these are symmetric or not. Now 1, 2 belongs to R1, hence 2, 1 should belongs to. 2, 1 should belongs to. Yes, it is. Hence it is. Now 2, 3 is there, so 3, 2 is also there. Hence this is the symmetric relation. Now come here, 1, 2 is there, so 2, 1 is there, 3, 4 is there, 4, 3 is there, so this is symmetric relation. Let's take the other type. Suppose we have 2, 3, 3, 1, 3, 2, 1, 4. See, we have 2, 3 here, 3, 2 here. We have 3, 1 here. Do we have here 1, 3? No. Hence, this is not the symmetric relation. Okay? Let's take more real-time examples on this. Let's see. Next example. Suppose set A is all straight lines in a given plane, and the relation here I am defining on the two straight line L1 L2 as L1 is parallel to L2, and the second relation I am defining here L1 L2 are such that L1 is perpendicular to L2. We have to check whether these relations are symmetric or not. Let's see. Two straight lines we have in a given plane, both are parallel. This is L1, this is L2, both are parallel. Now the symmetric relation says if L1 is parallel to L2, do we have L2 parallel to L1? Of course yes. Hence this is the symmetric relation. Now let's check for this. Two straight lines are perpendicular. This is L1, this is L2. Now L1 is perpendicular to L2, so L2 will be perpendicular to L1. Hence this is also the symmetric relation. Now let's check for it what we studied, reflexive relation. Let's check for that. Reflexive relation means two straight lines we have, L1 and L2. Do we have every straight line parallel to itself? Yes, of course. Then this is the reflexive relation as well. Now check for this. This is if L1 every straight line, do we have every straight line perpendicular to itself? Of course not, because this will make the 180-degree angle. Hence this is not the reflexive. Not reflexive. That's the thing. Okay. So this were some types of relation. Now the rest types of relation we will see in the next class. Thank you.